Welcome to Lecture 3.7, Fourier Transforms. Let's start with the definition of the Fourier transform, and then I'll try to convince you how and why this arises naturally. Suppose f is a complex valued function whose domain is the real line, and suppose f vanishes outside of some finite interval. So what I mean by that is the graph of this is 0 everywhere except for some finite piece. So this is the interval over which the function is not necessarily 0. Its Fourier transform, then, is defined as follows. So there's several ways to write this. Some books write this as a capital or a script f of little f. Think of this like the Laplace transform, which we usually write as script L of f. I won't use that notation very much. Usually I'll use this, f hat of omega. And you should think of omega as angular frequency. I'll explain that later. But now know that this is the integral from negative infinity to infinity of f of x times e to the minus I omega x dx. Now this is an improper integral. So technically, this is defined as the limit as L goes to infinity of the integral from negative pi L to positive pi L of f of x e to the minus I omega x dx. Maybe you were expecting this to be from negative L to positive L, though it really doesn't matter. It's actually more convenient if we stick a pi in here, and I'll show you why shortly. Next, I want to compare this to the definition of the Laplace transform, which I assume you've seen before. If not, that's fine. So the Laplace transform of a function f of t is the integral from 0 to infinity of f of t e to the minus st dt. Now, several comments. S is assumed to be an arbitrary complex number. So if that's the case, this isn't necessarily going to converge on the entire real line. We usually only get that it converges from 0 to infinity. That said, there are examples when it converges everywhere, and this might be called the two-sided Laplace transform. But in general, we can't expect that. So this is often called capital F of S, and S is thought of as frequency. And t is typically, or f is a function of time usually, whereas here x is a function of space. Time is typically half infinite, starts at say t equals 0 and goes forward, and space might be like an infinite ray, it might be doubly infinite on both sides. That said, there are plenty of examples of Fourier transforms of functions of time, and actually this is arguably more natural, but in our applications in this class, we will usually use them for functions of space. Okay, so finally, notice that if you think of S as a general complex number, then the Fourier transform is the Laplace transform is a special case of the Laplace transform. So if you take F and you plug in I omega, so a purely imaginary complex number, then you get, so I'm using this little f here, then I get f, the Fourier transform f hat of omega. And of course, this is if you restrict the integral, or if you extend the integral from negative infinity to positive infinity. Okay, so I won't go into this too much. I think later in the class we will solve PDEs using both Fourier transforms and Laplace transforms, and we'll typically use the Fourier transform if it's a function of space, and the Laplace transform if it's a function of time. Now I want to motivate this definition of the Fourier transform. So we already know that our function, by definition, vanishes outside of some finite interval, so let's assume that interval is negative pi L to positive pi L. What we're going to do eventually is take the limit as L goes to infinity. So let's suppose that we have negative pi L here and positive pi L here. Let's suppose our function is just a little blip, like a signal. So it's 0 outside of this interval. Maybe it's 0 inside some of the interval as well. And let's see what happens if we compute the Fourier series of this function. Now this is not periodic, but what we could do is we could extend this function to be periodic, of period 2 pi L. And if we do that, we can compute the Fourier coefficients Cn. And by definition, Cn is 1 over 2 pi L times the integral from negative pi L to positive pi L of f of x times e to the minus I n x over L dx. that's starting to look a little bit like this. Now, our original function is 0 outside of negative pi L to positive pi L. So original function, this integral is exactly the same if we replace pi L with infinity and negative pi L with negative infinity. I'm not talking about the periodic extension. I'm talking about the original function. In other words, this integral is exactly the same as this improper integral. The same thing, except we're integrating from negative infinity to positive infinity. Now, I want you to compare what this integral is to the definition of the Fourier transform up here. So if we set omega to be equal to, let's see, what is it? So here we have I omega x. So if we have n over L, so if omega is n over L, then this integral, at least what's inside the integral, is equal to this integral here, except now we have a 2 pi L on the outside. In other words, this integral is equal to 1 over 2 pi L times the Fourier transform of the function f, where omega equals n over L. So in other words, what we've done is I've taken this function that vanishes outside of some finite interval, and I've said, if we actually make this function periodic, then the Fourier coefficient Cn is 1 over 2 pi L times the Fourier transform of that function at n over L. So we have a formula for the Cn's, and now we're going to take the limit of this as L goes to infinity. Now this means that we can't quite write the original function as a Fourier series, but we can write the 2 pi L periodic extension of the function in a Fourier series. So the sum from negative infinity to infinity of Cn e to the I pi n over L times x. And we have a formula for Cn. It's this thing right here. And this is the infinite sum over all integers n of 1 over 2 pi L times the Fourier transform f hat of n over L times e to the I pi n over L times x. So what do you think comes next? Here's a hint. Riemann's sum. Now, let's let omega n be equal to n over L and delta omega equal 1 over L. So notice that omega n appears multiple times in both of these sums. Now I'm being a little bit sloppy because I've said that f of x is this function that vanishes outside of some finite interval, and now I'm saying f of x is this periodic function. But I assume that you're mature enough to be able to distinguish between the two. So the original f of x that vanishes outside of some finite interval really is what you get if you take this periodic function. Remember, that looks like this little thing, that periodic, and you take the limit of this. So let's take the limit of this as L goes to infinity. So if you do that, then this little window gets larger and larger, and everything out here just goes away as these things go off to infinity. So let's do that. Thus, the limit of this Fourier series of this 2 pi L periodic function is the original function that vanishes outside of some finite interval. So in other words, the original function f of x is the limit of this series as L goes to infinity. And particularly that series is Cn e to the I pi n over Lx. So let's plug in Cn. We have an expression for that right here in terms of the Fourier transform, and we will plug in n over L as well. So we get 1 over 2 pi, and there should be an L here, but notice that L is in this delta omega, because that's 1 over L. So here's our 2 pi over L. And then we have the limit as delta omega goes to 0 of the infinite sum of, so here's that, the rest of that Fourier transform, f hat of n over L, which is omega n, and then we have e to the I pi, now n over L is omega n x. So this is exactly what we get. We take this sum and we substitute in for Cn and for n over L. And this limit here, this is exactly a Riemann sum. This is 1 over 2 pi times the integral. The sum turns into an integral in the limit from negative infinity to positive infinity of f of omega e to the I pi omega x d omega. So again, this omega n turns into omega, and delta omega turns into d omega. And that's just basic integral calculus. That's the definition of an integral from a Riemann sum. So hopefully that should motivate what this definition of a Fourier transform is. Basically, if you have a function that has finite support like this, you can, and it's zero elsewhere, you can say, oh, we can pretend that this function is periodic with this really big period. And then as that period, 2 pi L or whatever it is, goes to infinity, these things go away. And if you take the limit of the Fourier series, you get basically a Fourier series, but instead of a finite sum of terms, you get a continuum of terms. And these coefficients, this is the Fourier transform. So think of it like a continuous version of a Fourier series. But look what I have here. Now I actually have the original function f of x written in terms of the Fourier transform. So suppose I were to give you this. I say, suppose that this is the Fourier transform, f hat of omega of little f of x. How can you recover the original function? Here's how to do it. I've just told you. The original function, f of x, is the integral from negative infinity to infinity of the Fourier transform times e to the I pi omega x d omega. You got to divide it by 2 pi. So this formula right here, this is called the inverse Fourier transform of f hat of omega. And sometimes we denote this as script f inverse of f hat, sort of like how the Laplace transform is sometimes denoted as L inverse of capital F. Let's do an example of a Fourier transform and a few Fourier series. So we'll use one of the simple examples I can think of, and this is probably the most common example in any book, paper, or website about Fourier transforms. It's a function that is not zero, but it's pretty close to being zero. So it's just a constant function for an interval of 1 and 0 everywhere else. So consider a 2L periodic function defined as follows, and I'll sketch this in a moment. So what we're going to do before I sketch it is we're going to compute this complex Fourier series for L equals 1, L equals 2, and L equals 200, and then compute its Fourier transform and compare all of these things. Okay, so here is this function. Let me sketch it. So I don't need very much room to sketch it. So this is, say this is 1/2, and this is negative 1/2. Then our function is 1 on this interval, and then it is 0 elsewhere, except just to make things easy, let's say that at this point of discontinuity, the function is 1/2. Okay, so for the first example, L is going to be equal to 1. So let me sketch that as well. So this is L, and this is negative L. So our function is going to be 1/2 here, and 1/2 here. And now we're going to make this thing periodic. So if we do that, then right here, this is 1.5. And I don't think I'm going to sketch that because I'm going to be thinking about a different L part of the time. Well, it wouldn't hurt to say this is 1.5, this is 2. You can think of that as 2. And then so forth. This is just going to repeat. So let me do that again here. Okay, so here's what this function looks like, and what we're going to think about is taking the limit of this L as it goes to infinity. So as we do that, that's not going to change the width of these signals. It's just going to change the width of the gap between them. Okay, so for example, if we were to compute this, or let me just sketch this for L equals 2. So we have the same little signal here, the same little jump. But now, instead of L being 1, L is going to be equal to 2. So we have this bigger gap between the signals. So this is negative 2. I'm going to say this is L equals 2 and negative L equals negative 2. And then we have to go a little bit further. And let me see if I don't think I even have, it's going to look like that. Okay, so this is what we're doing. Let's first compute the Fourier series of this first example. So let's start out with L equals 1. So now Cn is 1 over 2L, so that's 2 times 1. Let me write that in red. Times the integral from negative L to L, although we really only need to go from negative 1/2 to positive 1/2 because the function is 0 outside of that. So negative 1/2 to positive 1/2 times the function is 1 in that region. So times e to the negative I pi n x over L, and L here again is 1 dx. So this is 1 over 2 pi I n, the negative sign here, e to the negative I pi n x from negative 1/2 to positive 1/2. And if we, let's plug that in. So now we get 1 over 2 pi I n times e to the positive pi, or I pi n x over, well, x is 1/2, so over 2 minus e to the negative I pi n over 2. Now this time, let me remind you that the sine of x equals e to the ix minus e to the minus ix over 2I. So we have most of that right here, and then we have a 2I right there. So I'm going to write this as, I'm going to pull out the 2I as 1 over pi n, and then I'm not going to write it twice, but what I have left over is sine of pi n over 2. So sine of n pi over 2. And let me now remind you what that is. So here's the unit circle, n pi over 2 radians. These are located right here. So the sine is the y value, the imaginary value. So that's 0 here, 1 here, 0 here, and negative 1 there. So these coefficients, so let me write out what this is. Let's see, where do I want to arrange things? I'll do it over here. So C naught, first of all, that's 1/2 because that's the average value. And then Cn is, well, let's write down the first 4. So for each of these, we're going to have a pi n on the bottom. So I'm going to do the denominators first. So pi plus, so 1 pi plus something over 2 pi plus something over 3 pi plus something over 4 pi. And now what is that something? And n equals, again, when n equals 1, so that's 1, 0, negative 1, 0. So that's 1, I think I said it wrong, 1, 0, yeah, no, that's right, 1, 0, negative 1, 0, and then I think you can see the pattern. So plus dot, dot, dot. And now notice that when n is negative, so C negative n is the same thing because we plug in a negative n for this, a negative sign pulls out of the sign, and a negative n occurs here. So let me just remind you that this is, so Cn is equal to C negative n. So what I want to do now is I want to give you another way to think of this function with a graph. So this graph that I've drawn it here, this is a function of position x. And so this is f of x. And maybe it's better if you think of this as a function of time. I don't know. And let me just write that, or f of t. Because if I say time, I can talk about frequency as being things like cycles per second or radians per second. So maybe maybe, let me circle these and ask, should I put t here? So there might be times when I say things like per second, and obviously that doesn't make sense if I have x. So you might want to think of this as t sometimes. Doesn't matter. Anyways, this is a function. This is the graph of this function of f as a function of position or of time, whatever you want to think of that variable. We can also graph this function as a function of frequency. And let me do that now. So let me actually plot these CNs. So this is, so I want you to think of this now as n. I'm not going to write n because I'm going to actually call it something else. Actually, yeah, I'll write n because I'm going to divide it by something. You'll see. And now let's plot these CNs. So C naught is right here. So that's 1/2. So C naught is 1/2, and then C1 is 1 over. So this is C1, C2, C3, and C4. So C1 is about 1/3. I don't know, something like that. C2 is like that. C3 is like this, and then C4, and then I'm going to draw a couple more, and I think you can see what's going on. And then it's the same thing left of the y-axis. So there's C -1, C -2, C -3, C -4, C -5, and so forth. So think of this as a function of frequency. We're not at all telling you what the function is as a function of x. We're telling you only what the Fourier coefficients are. And this is enough to completely determine the function, given that it is periodic. Okay, so let's keep that in mind. And I think you probably see where I'm going with this. As L equals 2, we're going to fill in these gaps. And as L equals 100, we really fill this in, so it looks like a continuous curve. And then the Fourier transform, basically this graph of frequency, instead of having discrete points, is going to be a smooth curve. Okay, so let's now do L equals 2. Now I'm not going to recompute this integral, because I've highlighted in red where the only differences are. So if we do that, we get that, let's see, this difference here, let me box this. What's going to change? So instead of a 2 here, we're going to have a 4, because we're dividing by a 2 instead of a 1. And instead of a 2 here, we're going to have a 4. So for L equals 2, we're going to get that Cn equals 1 over 2 pi n times sine of n pi over 4. Now n pi over 4, if you go up to this unit circle, that's these things here. So basically what it's doing is it's taking twice as long to march around this circle. So what that means is that these Fourier coefficients here for L equals 2, let me put a line here just to distinguish this. So C naught's going to be the same, but now this is C2, this is C4, C6 is the old C3, and C8 is the old C4, and then there's going to be these things in between them that are given by these quarter radian points in the unit circle. So if I were to graph this in the frequency domain, now I don't want to make this n, because if I make this n, then these things are going to be stretched far apart. So what I want to do is I want to think of this really as frequency, which, remember in the previous slide, I'm going to also now use the top part. Remember when I said that let's let frequency or Fn be equal to n over L? Let's do that again. So let me say this is n over L, and I'm going to call that frequency. So now if I do that, I get the same thing. So now this is, so n over L, before when L was equal to 1, this is 1, this is 2, this is 3, this is 4, so this is 5. Think of this as radians per second, or again, that's why I sometimes like to use t, because I get cycles per second or radians per second. It's easier to say second than per unit distance. But now notice that I'm going to get exactly these same frequencies, both left and right, except now, oops, that's supposed to be on, and that's going to be over. So this here corresponds to C1, this is C2, this is C3, this is C4, this is C5, etc. But now this is C2, this is C4, this is C6, this is C8, and this is C10. And we're going to have these gaps that are in between. So the C1s, the C3s, these are going to be like this. So we're basically filling in this frequency spectrum, and we need to because the period is now longer. So we need a finer set of frequencies to capture this, the fact that we have twice as much length here. Okay, so now you can probably see what's going to happen when we get L equals 200. Well, if you don't, let me sketch it. And this is basically going to be indistinguishable from the Fourier transform. Is we're going to get this, I don't know how well I am at drawing it, this sort of dying sine function. And if L equals 200, I mean, if you want to think of it, you have all these tiny little pieces here of with omega. But I don't think I even need to. Well, yeah, I'll write it here. I want to save myself some room for the Fourier transform as well. So this is, so when L equals 200, maybe I'll put it over here. We get that Cn equals 1 over 200 pi n times sine of n pi over 400. Okay, so now let's compute the Fourier transform. And I'll show you how we're going to get something that looks like this. Okay, so I'll cross that out. I'm just going to say the Fourier transform, f hat of omega, is the integral from negative infinity to infinity of f of x e to the negative I n x dx. Now I'm going to actually make one little change. Instead of this being equal to, let's go up here. So I have this 1/2 here, and this 1/2 here, and this 1/2 here. And instead of this being equal to 1/2, I'm going to call it, I'm going to say let this be equal to a. And I'm going to compute this integral in terms of a, just because we have other 1/2s floating around here, namely in the bottom of this sign. And I don't want to get my 1/2s and 2s confused. So I'm going to let this be a. That doesn't change this 1/2. That 1/2, that's the height, half the height of this shelf. So that's not going to change. But now so what I'll solve this more generally for an a, and then I will plug in 1/2 at the end. I think that'll just be easier. It's also dividing by 1/2 is just annoying. Okay, so this is let's see. So let's write this as the integral, from negative a to a of 1 times e to the minus I n x dx. Let's move over here. So this is e to the, it's not nx, I should say it's omega x. I forgot about that. So I think I can turn that into an omega. So this is e to the minus I omega x over negative I omega from negative a to a. So this is e to the I omega a minus e to the negative I omega a over I times omega, which now again this almost looks like a sine. So I'm going to write this as a sine and pull out. So I'm going to pull out the omega and stick a 2 down here. So I got to stick a 2 up here as well. So this is 2 over omega times e to the I omega I a minus e to the negative I omega a over 2I. So this is, and let's see if I have that, let's see if I did that correctly. I think I did. So what is this? That's sine. There's actually a neat way I'm going to write this. I'm going to multiply top and, so I have an omega a here, and I have an omega on the bottom. So I'm going to multiply top and bottom by a. So let me do that, put a here and an a here. And now if I do that, I get 2a sine, to a sine of omega A over omega A. And this function actually has a special name. It's called the sine cardinal function, or just sinc, S-I-N-C. So I'm going to write this as 2a sinc of omega A. So this is the Fourier transform. And actually, if you plug in A equals 1/2, A equals 1/2, then what you get is, you get that f hat of omega is sinc of omega over 2. So that is what this little envelope function is. So it has height 1, well, almost. It has height 1, and this up here has height 1/2. So how do we account for that? Now, actually, I claim that we really should be multiplying this by 2. We should dilate it by 2L, and I'll explain that in a moment. So let me first do that. Let me multiply this by 2C0, and that's equal to 1. And now this is I'm going to say properly normalized to be like this. And to see why we should do that, let's compare what I wrote down here. So I said this was the same graph as this, and it's actually really not, because we've stretched out, we've increased L. Now the average value of this function is not 1/2 anymore, it's 1/4. So really this is 1/4 when I said it's equal to 1/2. So I should really say that this is 4C0 and make this equal to 1. And actually, because of that, these coefficients, I need to scale those as well. So I was slightly wrong when I said that C2 equals C1 and C4 equals C2 and so forth. I really should have said that 2C2 is C1. And I should have put 2's in front of these things, because we're going from L equals 1 to L equals 2. So now maybe I should say this is 2C1 and 2C2. I should put 2's in front of here, and I really should put 4's in front of here to make it. So now these things are properly dilated both horizontally and vertically. So that's the Fourier transform, and I really like this particular example because you can see it explicitly how it's constructed by taking a periodic function and then just letting the period go to infinity. And it also highlights something that's really important that I want to emphasize is, here's a function f. Think of this as a signal. We normally think of this as a function of position or a function of time, depending on what variable we use. But there's another way to think of it. It's a function of frequency. So these Fourier coefficients that we've seen, we haven't done this before. We haven't actually plotted them along the real line like this. And if we do that, you can see how this function is completely determined by these particular frequencies. And then as L gets larger, the period gets larger, those things get more filled in. And in the limit, passing from a sum to an integral, we get a whole continuum of frequencies. And if we do that, we can represent non-periodic functions as, again, a whole integral of frequencies. And that's, I think, really insightful. It takes a little while to get used to, but that's the whole idea of transforms, things like Fourier and Laplace transforms, going from the time or the spatial domain into the frequency domain. And engineers will go into this frequency domain, and then they'll play around with those frequencies, and then they'll pull it back into the time or spatial domain. And often that's useful for things like control theory or solving differential equations, or just getting insight into these systems. Now that we've finished that long example, let's summarize what we've learned. So think about a Fourier transform as a continuous version of a Fourier series, in that every continuous function from negative pi to pi, or if you prefer, every 2 pi periodic function, can be decomposed into a discrete sum of complex exponentials. That's the Fourier series. You sum over all integers n of Cn e to the I nx. And we have an explicit formula for the Cn's. Cn is 1 over 2 pi times the integral from negative pi to pi of f times e to the minus I nx dx. So you should think about the frequency omega here being n over pi. So pi is L. And I said continuous function. You can weaken this and just say piecewise continuous, and then there's issues at the point of discontinuity, but it's just easier for me to say continuous. Next, let's double the length. Let's go from negative 2 pi to positive 2 pi, and you still have a Fourier series. But now the formula for Cn is a little bit different. You divide by negative 4 pi, and you integrate from negative 2 pi to positive 2 pi, and you divide here by 2. So now think about omega as being n over 2 pi. So that's angular frequency. In the third example, let's extend this from negative 2 pi to negative 200 pi to 200 pi. We get a Fourier series representation of x as before, but now our formula for Cn is a little bit different. So where we had 4s and 2s up here, we have 400s and 200s here. And think of omega, angular frequency, as n over 200 pi. Finally, if we take the limit as this L goes to infinity, we get that every continuous square integrable function, more on this in a moment, on the real line can be decomposed into not a discrete sum anymore, but now an integral of complex exponentials. So now, instead of writing f as a discrete sum of complex exponentials up here, think of it as discrete harmonics. Now we're writing it as a continuum of harmonics. So the integral over the whole real line of, I'm going to call this c omega times e to the I omega x d omega. And we have an explicit formula for c omega. It's 1 over 2 pi times the integral over the whole real line of f of x e to the minus I omega x dx, which is just 1 over 2 pi times the Fourier transform f hat of omega. So none of this is new. We saw this formula 2 slides ago. It's just a slightly different way to present it, especially when thinking about this as a limit of what we know in the finite periodic case. We also learned about the sine cardinal or sinc function. This arose as the Fourier transform of this basic rectangle function. That's 1 on a small interval and 0 elsewhere. Actually, its Fourier transform is sinc of omega over 2, where the sinc function is defined basically to be sine of x over x. And we have to define it to be 1 at the origin because this is undefined there. Now this is called the sampling function in signal processing, and here's what it looks like below. Here's the graph. And what we did is we plotted frequency in the x-axis and the Fourier coefficients, or L times the Fourier coefficients, on the y-axis. And then we plotted the Fourier coefficients. So for some value of L, these are what the Fourier coefficients look like. Or I should say the scaled Fourier coefficients. And I think I'm not going to specify what L is here because this is actually sinc of x, not sinc of, or sinc of omega, not sinc of omega over 2. But for some value of L, this is what we get. And then if we double L, they become twice as dense. And so forth. And then in the limit, we get the sinc function. And that limit is, we're passing from a Fourier series of this function, which for some L, looks like that. And the limit, I'll get rid of that because it's ugly. Limit, we get this very smooth function. That's the Fourier transform. No lecture on Fourier transforms would be complete without mentioning that there are at least 4 common definitions of the Fourier transform that are all a little bit different. And it depends on who you ask. So if you ask someone who's a mathematician or a physicist or an engineer or from North America or from Europe, you might get different answers. And even within these groups, there's a lot of variation. So these are common enough that I should show you all of them. And I'm going to use what Marcus Pavato, the author of a great book on linear PDEs, calls them. He says these are the evil twins of the Fourier transform. So I like that terminology and I'm going to use it, but actually my definition of the Fourier transform that I've showed you is actually one of his evil twins. So this is our definition of the Fourier transform and the inverse Fourier transform. Notice that they're the same except there's a 1 over 2 pi in the inverse, and there's a negative here and a positive here. Next is the so-called opposite Fourier transform and its inverse. So this is the same except now the 1 over 2 pi goes on the forward Fourier transform and not the inverse. Now Marcus Pavato, who, as far as I know, coined the term evil twins, switches not only the names of these things, but also the notations. So just heads up. Now, for all of these, the Fourier transform is what takes you to the function of frequency, and then the inverse Fourier transform is literally the inverse of that. So I'm going to call this f, and this is f inverse. So these things, like derivatives and integrals, they undo each other. They're inverse functions. The so-called symmetric Fourier transform and its inverse, this is for people who like to be egalitarian, who like everybody to get along. They say, let's just take this 1 over 2 pi and split it up between the Fourier transform and its inverse. And finally, we have the so-called canonical Fourier transform and its inverse, which I'm going to use the variable c for. I'll explain why in a moment. So the Fourier transform is now the integral from negative infinity to infinity of f times, it's a little bit different here, e to the negative 2 pi I c x dx. And the inverse transform is the same thing, except now we have to make this positive exponent instead of negative. Finally, we have the so-called canonical Fourier transform and its inverse. I'm going to use the variable c for this instead of omega, and this is the integral over the whole real line of f times e to the minus 2 pi I c x dx. And its inverse is the same, except now instead of a negative sign, we have a positive sign in the exponent. This last definition is motivated by the relation between angular frequency omega being 2 pi times oscillation frequency c. So what I mean by this is, suppose you're going around a track and you go around once, that's 2 pi radians, say, per second. Compare that to, if you go around once, that's 1 cycle per second. So there's that factor of 2 pi. This is probably the most common definition, and if you look at Wikipedia or Wolfram Math World, that's the definition they're going to use. All of these have their pros and cons. Now, most books will actually use c for the variable in all of these. I don't like that at all because for these definitions, they really are in terms of angular frequency. And I think physicists will typically favor one of these first 3 definitions, although really all of them are common. You'll see them all over the place. It is quite easy to go between these definitions. So the Fourier transform of omega is 2 pi times the opposite transform of omega, which is root 2 pi of the symmetric transform of omega, which is the canonical Fourier transform of omega over 2 pi, or of c. So all of these have their advantages and disadvantages. Most books will actually use c for all of these variables. I think that's a little bit odd because I like using omega when angular frequency is the physical definition of this. And I think the last one is probably slightly more common because if you look at Wikipedia, that's the one that's won out there. Although it just depends what formulas you're dealing with. Sometimes a formula for one of them is going to be really nice and you have no constants lying around, but another formula is messier. And I think the best thing I can compare this to, many of you have heard about tau. Tau day is June 28th. And tau is equal to 2 pi. And there's a bunch of people on the internet that believe that tau is a better constant than pi. It's more natural because, and you can watch these videos that are like 1 or 2 minutes long that show you a whole bunch of formulas that are much nicer if you use tau instead of pi. Like, for example, the circumference of a circle, instead of being 2 pi r, is just tau r, or 2 pi r. So which one's nicer? Obviously, you don't have a 2 out front. However, what they don't tell you is that there's just as many formulas where pi is nicer. So like, what's the area of a circle? That's pi r squared. Now, if you use tau, and tau is equal to 2 pi, then that's going to be pi tau squared over 4. And that's not as nice. So take your pick. Any of these work. It's a little bit annoying because you have 2 or 3 books and you might have 2 or 3 versions, and comparing the formulas, you got to be really careful, especially because it's normally really, really hard to not be off by a factor of 2 here and there. And this makes it even harder. So just a word of warning, all 4 of these are used commonly. We're going to stick with this one, but you might see all 4 of these in your academic careers. I want to conclude with a few more words about the Laplace transform of a function, f of t. Recall this is the integral of f of t times e to the minus st dt. It's usually over the half real line, sometimes over the whole real line. A lot of functions, this integral is not going to converge over the whole real line. That's why we have to restrict it. To get the Fourier transform of this same function, all we do is we just take the Laplace transform and we plug in I omega. So it's the integral over the whole real line of f of t times e to the minus I omega t dt. So we just get f of x and evaluate it at I omega. Because of this, these two transforms share many similar properties. So most of you learn about the Laplace transform first, so I'm just going to review these properties. The first of these is linearity. This should be very familiar to you. Both of these transforms are linear operators between vector spaces. So if we have a function in the time domain, which is c1f1 plus c2f2, and we apply the Laplace transform, we get c1 f1 hat plus c2 f2 hat. The next one is a time and phase shift. So if you have a function f of t minus a constant t naught in the time domain, that's a time shift, and you apply the Laplace or Fourier transform, let's do the Fourier transform for all of these, then you get the regular Fourier transform, f hat of omega times e to the minus I omega t naught. So this is a phase shift. You're multiplying a complex exponential to get a different frequency. The next property is in some sense a dual to this previous one. Shifting in the time domain is multiplication in the frequency domain. If you multiply by an exponential in the time domain, e to the I nu t f of t, and apply the Laplace or Fourier transform, you get the transform of omega minus nu in the frequency domain. Now this is a common thing. If you do action A in the time domain, and you get action B in the frequency domain, then generally if you do action B in the time domain, you get action A in the frequency domain. The next property is dilation by a positive number c. So in the time domain, if you have f of ct, that just dilates the graph by a factor of c, and you apply the Fourier transform, then in the frequency domain, you get 1 over c times Fourier transform of omega over c. The next example you've seen before for Laplace transforms. That's differentiation. So if you have a function in the time domain, f of t, and you take its derivative and apply the Laplace transform, then what you get is the Laplace transform of omega times I omega. So in other words, derivatives in the time domain carry over as multiplication in the frequency domain. Now, as I said, you've seen this with Laplace transforms. If you do this, you get the Laplace transform of f times s. And this should be no surprise. This relation between s and I omega, you've seen that up here. The Fourier transform is just the Laplace transform where s equals I omega. The next property is dual to differentiation, just like how the time and phase shift is dual to multiplication. So the previous one, derivatives in the time domain corresponded to multiplication in the frequency domain. And now this one is the reverse of that. If you multiply by t in the time domain, that carries over as a derivative in the frequency domain, a negative derivative. And finally, the last property is that of convolutions. So recall what the convolution of f1 and f2 is. That's the integral of f1 of t minus tau times f2 of tau d tau. And if you apply the Fourier transform of that, you get the product of the individual Fourier transforms of f1 and f2. So that's a really nice property. And I should conclude by saying that all of these properties, or I should say many of these properties, are slightly different depending on which version or which evil twin of the Fourier transform you use. Now, some of the basic ones like linearity or time and phase shift, it does not matter. Differentiation, same there. But things like convolution, if you use the opposite Fourier transform, you get a 2 pi out in front. I forget if it's a 2 pi over or a 1 over 2 pi. And so things are a little bit different. You have to be a little bit careful. And I know it's a little bit irritating, but that's life. Our next lecture will be our last one on Fourier series and Fourier transforms. And it's got a fun title, Pythagoras, Parseval, and Plancherol. So it's all about 3 classic theorems, and I guarantee you know one of them. The ancient Greeks knew this one, Pythagorean theorem, and I'm going to show you how that generalizes to the world of Fourier series and then Fourier transforms. So it's really cool. I hope you stay with us.